Hey gang, we are on chapter 8.1 on metabolism and thermodynamics, and we are going to actually get into some reactions happening inside of cells this chapter, and we get into some pretty heavy topics on what drives everything that happens in our cells. But anyway, I wrote down the key terms from this section here on the left side to make sure that you understand these things. And I've got a picture here of an assembly line, so it looks like a Volkswagen Bug assembly line over here. And the reason I have this is for this first term, metabolic pathway here. Metabolic pathway inside of a cell is going to be a series of reactions that are linked together, taking a molecule and turning a molecule into a different molecule, doing a reaction to it to turn it into a different molecule again, and doing another reaction, another reaction, another reaction. And that's a metabolic pathway. In the case of this Volkswagen Bug here, you can see that the first step in our metabolic pathway, it looks like they have a chassis down here, and they're doing something to that, but there's something happening at this location, and we're going to call that location enzyme 1. I'll talk about enzymes in a moment. Then it's going to move from this location to a new spot, location 2, and we're going to say that's where enzyme 2 is. And a different thing happens there, and it's going to change our thing that we've assembled. It's going to add a body to it and doing another job, and it's going to move on down the assembly line step by step by step until we get our final product, whatever it is we happen to want. Metabolic pathways can either assemble something like this one, or they can take them apart, which would be kind of the reverse of this. All right? If I look in an organism and take every single reaction that happens inside that organism, that's going to be the metabolism of that organism, or if it's a cell, the metabolism of that cell. It's every reaction that's happening inside of there. Usually those are within metabolic pathways. Very seldom would a cell do a reaction without it leading to another reaction and then to another and another and so on. But those are metabolic pathways. These enzymes are basically just machines. They're actually proteins, but they're machines that are doing a specific role, causing a specific reaction, causing a specific reaction, and we call them a catalyst. The reason we call them a catalyst is something that makes a reaction happen faster. An example of that, I used to paint water towers, and the paint that we would put on these water towers had two parts, a part A and a part B, and the part B we actually called the catalyst. The part A had all the pigment and all the color that you wanted, and if you were to paint with just the part A, it would never ever dry. It would just sit there on the tank and never dry. But if you added the part B to it, it would immediately start to dry. So you actually had a couple hours you had to use up that paint once you added the catalyst to it, because it would cause the paint to start to dry. So it basically speeds up a reaction. These enzyme catalysts then, another little tidbit about them is they can be reused over and over and over and over again, kind of like this spot on the assembly line. It doesn't do one thing and then it's done. It is actually used over and over again. So last little note here. The pathways within metabolism, within the all of metabolism, we can basically either break things apart or put them together. If we break something apart, it's called a catabolic pathway, and if we put something together, it's called an anabolic pathway, pathway. The reason, or the way that I remember the two of these, an anabolic pathway, if you ever remember reading or hearing about anabolic steroids, and that's what people in Major League Baseball were getting busted for using anabolic steroids, human growth hormones, things like that, but they would build up muscle, and anabolic pathways build up molecules. That's how I remember that. So we'll leave it at that. What we're going to find is these catabolic and anabolic pathways, whether they happen or don't happen or things like that, it's all driven by some energy concepts. And so the next slide, we're going to take a look at some energy concepts to explain all that. So here's some basics on energy here, and I put this picture on here. I gotta be honest, this is just a stupid picture, and it doesn't. I'm not even gonna talk about it, but I felt like I had to put a picture in here. So here you go. Energy is the capacity to cause change. You would have learned about it in other classes as the ability to do work. It's like, what in the world is work? So energy is the capacity to cause change in things. It takes energy to change things. And we're going to look at basically two different types of energy, although there's a lot more than this. The first one is kinetic energy, which you always learned as energy of motion. You'd remember that. What I need you to do to lock into your brain right now is that when we talk about kinetic energy in a cell, most of the time we're going to be talking about heat, okay? And heat is thermal type of energy. It's the movement of energy due to temperature differences. But basically, we're going to find out that heat inside of a cell, inside of an organism, is basically useless or wasted energy. But heat is a type of kinetic energy. So that's all you need to know for now. And then the other one is you would have learned about potential energy over the years, and potential energy is stored energy. It can either be stored like, I'm going to talk about this stupid picture, stored like this diver, he's up in the air and his position above the earth is, there's energy stored in his position above the earth. The way we talk about potential energy in a cell is as chemical energy. Okay, so those two words are going to go with each other. And the place where chemical energy is always stored in a cell is if here's two atoms or two molecules that are bonded together. This bond is where we store chemical energy, okay, and it's holding the position of these two particles together, so that bond ends up being chemical energy, a place where we can store energy. As a quick relationship to the previous slide, if I am taking two separate molecules and putting them together, that's a anabolic pathway, and I'm making a bond, which means it's going to require energy. Okay, it's going to require an input of energy to make this bond. If I were to break this bond and separate these two things, there's energy in that bond, potential energy, and I would release that potential energy. It could be taken off to do work somewhere. So that's some basics on energy, but the big thing is make sure that you think of chemical energy and bonds as being potential energy. It's probably the big one, and that heat is a type of kinetic energy that is kind of a wasted form of energy inside of a cell. So now we're going to talk about the study of energy changes within an organism. It's called thermodynamics, and thermodynamics is what drives all reactions, so we'll get into that here. And here's our brief overview of thermodynamics. Again, thermodynamics is the study of energy changes or transformations within an organism. There's a couple of laws, first and second law of thermodynamics. The first law of thermodynamics says that the energy of the universe, the entire universe, the energy of the entire universe is constant and has always been the same, will always be the same, will never increase, will never decrease, okay? And what that means is you can't, if you've heard of this one, energy cannot be created or destroyed. It is constant, okay? And so this first law of thermodynamics, this picture down here with the cheetah eating whatever it is that it's eating, and the idea here is this cheetah is going, if it wants to use energy, it has to get it from somewhere, so it has to eat food. You guys know that for sure. But it doesn't mean that anytime we do any reactions or anything like that, that if energy displays itself, it has to have come from somewhere and it has to be going somewhere. Okay, so that's that first law of thermodynamics. The second law of thermodynamics then is the one that starts to, it's going to get a little more complicated when we get into the next section. But the first law of thermodynamics, when it says you can't make any new energy or get rid of it, it does allow that you can change the type of energy. So you could change kinetic energy into potential energy, or you could change potential energy into kinetic, something like that. And this is where the second law of thermodynamics comes in. The second law of thermodynamics says that any time that we change energy from one form to another, we are going to create disorder. Things are going to get messy. We're going to create disorder. The word for disorder is entropy equals disorder. Okay, and so what they're showing down here with this cheetah is that it had energy stored in it, and it's going to transfer that energy apparently into some kinetic energy. And as it's doing that, it's actually taking molecules and breaking them apart, molecules that were ordered, and now they're becoming disordered, and so they become molecules of CO2 and H2O that are just kind of floating around in space, okay, or in the air, which is less ordered than when they were held inside of this cheetah. Okay, if we look at the energy, okay, so that was looking at actual molecules. If we look at energy, energy was actually being held nice and orderly in some molecules. It was held as potential energy, and now it's being released as heat. Okay, and heat is energy that is just scattering everywhere. Okay, it's not very useful. So we are in this location. We're actually increasing the entropy of the universe. Okay. To add to this, if we have a reaction, just another term that shows in here, if we have a reaction that is called spontaneous, I shouldn't write the whole thing here, but spontaneous, that means that it will. Is that how you spell spontaneous? I don't know. Anyway, that means that that reaction, it doesn't mean it's just going to automatically happen, but what it means is that that is a reaction that will increase entropy. Okay, there are reactions that don't increase entropy, and if you have a reaction that does not increase entropy, that means you have to take energy from somewhere else and use it to create order. And in order for that to happen, that means that somewhere else in the universe there would be disorder being created or entropy being created. So we're going to end it at that. That's basics on metabolism, thermodynamics. Get into the next section, 8.1, and we're going to put a little bit of math behind this energetics thing and this thermodynamics thing. So hopefully this was good for you, and we'll see you later.